I will start in 2-3 minutes. I'll start in 2-3 minutes. Okay, so I'll share my slides. So this is the 7th live session of the course Structural Biology. And uh, I will be covering more about different spectroscopic methods like IR, Raman, UV spectroscopy, and so on. So this is kind of to revise what we saw in the previous class, is that when a ray of light falls on a surface, there can be many different events. One is transmission, where the ray passes through without any deviation. One is reflection, where it reflects back into the original media. Another is refraction, where it passes through the second media but with a change in angle. Another is diffraction, where light passing through a split uh, scatters in different regions. Another is absorption, where it is absorbed by the region where it is striking. And finally, you have scattering, which is similar to diffraction, but diffraction was occurring through a slit, and scattering occurs when it hits any media. So these are the different kinds of phenomena that can occur when a ray of light hits any surface. And there are optical instruments called spectrometers, which can be used to study different phenomena in light. These spectrometers basically measure the wavelength or frequency of light which is being emitted or absorbed. And the result is that you will get a spectra like this, which is like the fingerprint of a particular substance. So here you have many different compounds. You can see each compound has a very unique spectra. This particular thing shown here is the um, frequency on the x-axis. You can see that each compound has different peaks, meaning it is absorbing at different wavelengths or frequencies. So this spectra is kind of like the fingerprint of a compound, which is unique for each compound. So to go into the basics of spectroscopy, Sir Isaac Newton in the later half of the 17th century showed that when white light passes through a prism, it breaks up into the 7 colors. Then in the 20th century, there was a debate between whether light has particle nature or a wave nature, and different scientists supported different models. Now we know that light has both nature, both as it behaves as a particle in some cases and as a wave in some other cases. Scientists understood that the dark and bright lines seen in absorption and emission were uniquely characteristic of the internal makeup of chemical elements. So you can see that you have many different energy levels in an atom, and when there is transition from one energy level to another, you will see that particular line in the spectra. So this first spectra shown here is a emission spectra, where only this particular light of this particular wavelength will show up as a bright line. So imagine level 3 to level 1. So this line, level 3 to 1, this is showing up here. 2 to 1 is showing up here. 3 to 2 is very small, so the energy might not be visible in the range we are seeing, which is what is happening here. The point is that in emission spectra, the entire spectra will be dark, and only those wavelengths at which emission is happening will appear as a bright band. And this spectra, which is shown below, is the absorption spectra, where you will see a very bright spectra, and only at the wavelengths where absorption is happening, a dark band will appear. So it is like the reverse of the emission spectra. You can see from absorption level 1 to 2, this is this band, and level 1 to 3 is this band. So everywhere else is a bright pattern, only where the wavelengths at which the absorption is happening, you will get dark bands. So that is the absorption spectrum. So scientists had understood at that time that the energy in light is somehow exciting the internal motion of atoms and molecules, extracting energy from the light at certain wavelengths, giving rise to these lines. So basically the atoms or molecules are getting excited by light at particular wavelengths, and they are going to higher energy levels. Similarly, energy could excite internal motions in matter, which would then radiate away the absorbed energy as light, accounting for the bright or emission lines in the spectra. So when it is the emission spectra, the light of the wavelength which is being emitted appears as a bright line. Just 1 second. Right, so I'll continue. So this is the electromagnetic spectra we have seen in previous classes also. There are various regions of the spectra. So from high to low wavelength, the radio waves have the highest wavelength, meaning the least energy. Then is the microwave, then infrared. Visible is in a very short range. Then ultraviolet, X-ray, and gamma rays have the shortest wavelength, meaning the highest energy. So electromagnetic spectrum is made up of different kinds of waves like this. We had seen previously that for NMR, we were focusing on the radio waves. Here we will see how different regions of the spectra are used for different kinds of spectroscopy. So we'll just briefly look into the different regions of the electromagnetic spectrum. Firstly, the radio waves. The radio which is used in everyday life it captures these radio waves emitted by the radio stations. And radio waves are also emitted by stars and gases in space. The wave in this region of the electromagnetic spectra finds application in NMR spectroscopy, which we have seen in the previous class. Then you have the microwave radiation, which is used in microwave ovens for cooking or by astronomers to learn about the structure of nearby galaxies. They find application in rotational spectroscopy, which we will see in this class. Then you have the infrared region of the spectra, which is associated with molecular vibrations. So if you supply energy in the infrared region, the bonds will vibrate. It is used for infrared and Raman spectroscopy. Again, we will go through this in this class. Then it's a very narrow region of visible light, which our eyes can detect. And these are involved in the electronic transition. So excitation of electron from one state to the other state is done by visible light. Ultraviolet region is also involved in electronic transition. So electronic spectroscopy makes up visible. So for electronic spectroscopy, we use light in visible and ultraviolet or UV range. And finally, the X-rays, which cause transition in the electrons of the molecules. We have studied that these are used for X-ray crystallography. If you remember that when an atom is excited by X-rays, it knocks out one of the internal electrons of the atom, and one of the electrons in the outer shell jumps to take its place. So X-rays basically cause transitions in the internal electrons of the molecule, and they are used in X-ray crystallography. The basic property of all electromagnetic waves is that they are created by accelerating electric charges. If you imagine a charge moving up and down with a simple harmonic motion, and you know moving a charge that has a motion will emit a wave. This is the electromagnetic wave basically. So this is basically the electromagnetic wave that is being emitted by a vibrating charge, and the frequency of the wave will be the frequency at which the charge is vibrating. And in an electromagnetic wave, the electric and the magnetic fields are perpendicular to each other, and the direction in which the wave is traveling is perpendicular to both the electric field and the magnetic field. Now, to create light waves in the visible part of the electromagnetic spectra, one second. My screen is frozen, just 1 second. Now, to create light waves in the visible part of the electromagnetic spectra, the wavelength must range from 0.4 to 0.7 micrometer. And for that, the charge must accelerate at a high enough rate to generate waves within this wavelength. So how can we calculate the frequency of the charge? The general formula we know is that velocity of any wave is the frequency into the wavelength. And so using this formula, we can calculate what should be the frequency at which the charge is vibrating, so that the wave generated has wavelength within the visible part of the spectra, which is between around 400 to 700 nanometer, that is 0.4 to 0.7 micrometer. So to calculate the frequency at which the charge must vibrate in order to generate waves in the visible part of the spectra, we will use this formula V equal to F lambda, where V is the wave speed in meter per second, F is the frequency in hertz, and lambda is the wavelength in meters. So for all light in vacuum, the speed of light we know is 3 into 10 to the power 8 meter per second. And if we consider a wavelength around in the visible range of light around 0.5 micrometer, then using the, so V equal to F lambda, if we take lambda to this side, then frequency will be velocity divided by wavelength. So to find the frequency, we will divide the velocity, that is 3 into 10 to the power 8 meter per second, divided by the wavelength, which we have taken as 0.5 micrometer. we can see that the frequency is 6 into 10 to the power 14 hertz, which is an extremely high value. So the charge must vibrate at such a huge frequency, 6 into 10 to the power 14 times per second. It must vibrate so that it can generate an electromagnetic wave in the visible region of the spectrum. And this kind of high frequency is only observed in regions inside atoms and molecules, where the electrons move very rapidly around the nucleus and the atom can vibrate and oscillate very rapidly. So only within atoms and molecules you will get a frequency of such high value. That is why this within atoms and molecules, electrons will move at such high frequency. So that is associated with visible light, and that is why visible light can be used for electronic transition in the molecule. Because when you are supplying the visible light to the molecule, the frequency of the light matches the frequency of at which the electrons are vibrating, and so the electrons will be able to interact with the visible light and get excited to higher energy level. So visible light can be used in electronic spectroscopy. So here you can see, this is kind of an illustration to explain how from a moving charge you can get a wave. So here there is a AC power supply connected to the upper and lower arm of the antenna. So this is the upper arm of the antenna, this is the lower arm. And electrons are moving through the antenna. So this is the direction of movement of the electrons. Now, as the electrons are moving downwards, they are accelerating downwards. So electron is a charged particle and it is in motion. So an electromagnetic field will be created, which is moving outwards from the AC power source. And the direction of the electromagnetic field will be the same as the direction of motion of the electrons. So electrons are moving down and the electromagnetic field direction is also downwards. So like that, one wave will be generated. Now, if you change the AC voltage polarity, so AC is alternating current. So if you change the voltage so that now electron is moving upwards, the direction of this wave will also change to upwards. And this newly produced electric field created next to the antenna, shown by these lines, so you can see as one wave is being produced, it is moving outwards, then the next wave is being produced. So like this, you will have a series of waves being produced which can be received by the receiving antenna. So this is how a moving charged particle, in this case an electron, will generate an electromagnetic field. Now, in order to interact with the electromagnetic radiation, the molecule must have some electric or magnetic field that can be influenced by the radiation. So the radiation has both electric and magnetic field in perpendicular direction. So the molecule must also have some electronic or magnetic property to interact with the electromagnetic wave. In NMR spectroscopy, we have seen that the nuclear spin has magnetic dipoles, which in absence of the field, they are randomly oriented. But when you are providing an external magnetic field, the magnetic dipoles can orient themselves in the same direction as the field, in which case we will get a lower energy state, or they can orient themselves in the opposite direction of the field, in which case we will get a upper energy state. So in NMR spectroscopy, the interaction of the electromagnetic radiation with the magnetic dipoles of the nucleus causes a splitting in the energy levels. And we have seen that as we increase the magnetic field, the splitting of energy between the upper and lower levels also increase. So in NMR spectroscopy, the nuclear dipole is interacting with the external magnetic field that is supplied. Now, in case of rotation of a molecule which has a net electric dipole moment. So imagine this CO2 molecule which is rotating, and since CO2 you can, so in order to study this rotation of the molecule, we use microwave spectroscopy. Now, in case of vibration, the bonds are vibrating. The C and O bond can stretch outwards and inwards. We will go into the details of all this as we go along this class. So to cause vibration in so the vibrational spectroscopy, where the bonds of the atoms vibrate, that is studied using IR radiation. And finally, you have electronic transitions, where the electron is excited from lower state to upper state in absorption spectroscopy, or excited electrons come down from upper state to lower state in emission spectroscopy. For electronic transition, we have seen that we use wavelengths of ultraviolet or visible spectroscopy. So there are different kinds of spectroscopy that use different regions of the electromagnetic spectra. NMR spectroscopy uses the radio waves, rotational spectroscopy uses microwaves, vibrational spectroscopy uses the IR region, and electronic spectroscopy uses both UV and visible region of the electromagnetic spectrum. Now, there are different kinds of spectra that you can obtain. One is the continuous spectra, where white light passed through a prism is just focused on a detection plate. So we know that when white light passes through a prism, it breaks up into 7 colors. So the continuous spectra is basically those 7 colors, one after the other. Now, absorption spectra is where you have the continuous spectra, but at the wavelengths where absorption is happening, you will get dark bands. So imagine this is a lower state of the electron, and this is the upper state of the electron. Now, at particular wavelength, that is particular energy values, the electron is getting excited from lower to upper level. So that particular wavelength is being absorbed, and that will appear as a dark band in the absorption spectra. The emission spectra is the exact opposite, where the entire spectra is black, but wherever emission is happening, that is from upper it is coming down to lower level, those particular wavelengths or those particular energies are appearing as bright bands. So emission spectra and absorption spectra are opposite of each other. So this kind of transition will happen only if the energy provided by the electromagnetic radiation is the same as the energy difference between the two states. So the energy difference between the same two states, delta E, must be equal to the energy of the electromagnetic radiation, which is h nu, where nu is the frequency, and we know we can write frequency as c by lambda, where c is the velocity of light, lambda is the wavelength. So the molecule will precisely absorb the radiation of wavelength lambda, and where it is absorbing, a dark line will appear in the absorption spectrum. But in reality, it is not one particular wavelength that is being absorbed, but a slight range in wavelengths. You can see this is a real absorption spectra. You can see actually a small range of wavelengths, delta lambda, is being absorbed. So the absorption line is not sharp, but appear as broad peaks. So there are different reasons that contribute to this broadening. The first is the instrumental factors. Consider the transition occurs at a wavelength lambda t. Now, in a short wavelength range, lambda t plus delta lambda or lambda t minus delta lambda, the slit will allow the radiation to pass through. So imagine you have a slit here and the radiation is passing through the slit and interacting with the particles. So you can see the main wavelength that is responsible for exciting the electrons is lambda, which is the big peak here. But a small range of wavelength, delta lambda, will still be allowed through the peak, because instruments are never perfect. So it can never be that the instrument is allowing one single wavelength to pass through it. Instrument will allow a small range of wavelengths, delta lambda, to pass through it. And so instead of the emission line being sharp like this, there will be a slight broadening that will be caused, because through the instrument slit, a small range of wavelengths is being allowed to pass through it. So that is the instrumental lack in the instrumental precision that is causing a broadening. The second factor that causes broadening are due to the sample itself. So molecules in a liquid or gaseous sample are in motion and they keep colliding with each other. You can see this is a gaseous, if we assume this is a gas, they are moving. And so as I was saying, another reason for broadening of spectra is due to the sample itself. Now, molecules in a gas will randomly move and collide with each other. And due to this collision, the vibrational and rotational motion of the molecule is affected. And if that is affected, there will be a broadening. So this kind of broadening, which is due to the vibrational or rotational motion in the molecule caused by collision of one molecule with another, is also known as Doppler broadening. And because of this, you can see if the perfect emission spectra, if we cool the gas down at very low temperatures such that we can assume the gas particles are at rest, the emission spectra has sharp lines. But as we increase the temperature, the gas particles are moving around randomly, they are colliding with each other, and that is affecting the vibrational and rotational motion of the molecule. In that case, there is a certain broadening that is observed, you can see, compared to the sharp lines, and this is due to this thermal motion. So this kind of broadening is due to the sample itself. The final reason of the broadening is also called intrinsic or natural broadening, and it arises from Heisenberg's uncertainty principle. So one form of the Heisenberg's uncertainty principle states that delta E into delta T greater than equal to h bar by 2, where h bar is h by 2 pi, h being the Planck's constant. Delta E is the uncertainty in energy and delta T is the lifetime. So an energy state where uncertainty is low, so it is only one energy, then you can expect that you can see this energy state is shown as a sharp line because the uncertainty in energy is low. So if uncertainty in energy delta E is low, then the lifetime will be very high. That is, delta T will be high because the product must be a constant. Or if we have a state where you can see this energy state shown by red is not a single line, it is a kind of range of energy because the uncertainty in energy delta E is high. So if uncertainty in energy is high, then the lifetime becomes short by the Heisenberg's principle. So in general, the energy levels we have is somewhere between the red and the green, which is shown in blue here. So there is a certain lifetime of that level, of that energy state, and according to the length of that lifetime, there is a certain value of uncertainty in the energy level. Because of this uncertainty, broadening happens, because now instead of there being a transition, so imagine there was no uncertainty, so there are two energy level, there is only one wavelength of transition. But now because there is uncertainty, there are multiple energy levels, and so one transition can be like this, one can be like this, so on. And so instead of one single peak, here it would be one single peak, here there is a certain broadening happening due to this uncertainty. So this broadening is called intrinsic or natural broadening. A spectrophotometer is an instrument that measures the amount. Yes.
Why there is uncertainty?
So this is actually part of Heisenberg's uncertainty principle. Any energy level, it will have a certain lifetime. And Heisenberg's uncertainty principle says that the product of this lifetime into delta E, that is the uncertainty in energy, it has to be greater than equal to this constant value. So this is kind of like this is like, you know, in Heisenberg's uncertainty principle, you can never know, you can either know the position or you can know the momentum. You cannot know both. So, and this is another form of the Heisenberg's uncertainty principle, which states that any energy level will have a certain amount of uncertainty in the energy. So this is actually like the derivation of this is too complicated, but you can just remember that any energy level, delta T will have a certain value because delta T is the lifetime. So any energy level has a certain lifetime. And so delta E must also have a certain value. It cannot be 0. So because of this, this is the natural uncertainty that occurs for any energy level.
Okay.
Okay. Now, the spectrophotometer is an instrument that is measuring the amount of light absorbed or the intensity of color at a given wavelength. Basically, any spectrophotometer consists of a source of light or other electromagnetic radiation, a dispersive element like a prism that will split up the light into different wavelengths. Then there will be a slit which will allow light of a particular wavelength or range of wavelengths to pass through. And once this light passes through the sample, a detector will detect it. So this is the basic setup of any spectrophotometer. Now there are certain terms. One term is called transmittance, which is given by I by I0, where I is the intensity of light after it has passed through the sample, and I0 is the initial light intensity. So I0 is always greater than I, so T is less than 1. Absorbance is basically, it is another term which is defined as minus log of transmittance, or minus log, if you write out T, minus log I by I0 is absorbance. So these are different terms that are defined with respect to absorption of light.
Ma'am, so this I and I0, the I0 is after the sample, means the wavelength, sorry, intensity after the sample, the light is passed through the sample.
It's opposite. I0 is the initial. You can see I0 is the initial light. I is the one after it passes through the sample.
Ma'am, means in the above diagram, it is after that slit, I0,
Yes, yes, yes.
not
Uh,
the light after that light source.
no, no, no. Uh, Here you can, so this is the sample, right? So
Mm.
I0 will be here before it
Mm.
reaches the sample, and I will be here, which the detector is detecting.
Okay, ma'am. Mm.
So there is something called a Lambert's law, which states that when a ray of monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the length of the absorbing medium increases. You can understand this practically. As you increase the length of this sample, intensity of the light will graduate, the light that is being transmitted after the sample, intensity will decrease, because greater the path length, more absorption is happening. And so here you can see a plot has been shown that when you have higher path length, the absorption is higher. In the y-axis, absorbance is being plotted, and in lower path length, which is this, the you can see as the path length is increasing, absorbance is increasing. And there is something called Beer's law, which says that when a monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the concentration of the absorbing medium increases. This also makes sense because when the concentration increases, you have more molecules which are absorbing. So if you are passing the light through a highly concentrated solution, then the intensity of the transmitted light will be lower because more molecules are absorbing. These two laws put together gives the Lambert-Beer's law, which is absorbance is ALC. A is often written as epsilon. So A is capital A is the absorbance, which we defined in the previous slide as minus log of transmittance. L is the path length in centimeter of the sample. C is the concentration of the sample in mole per liter. This small a, often written as epsilon, is called the molar absorptivity or extinction coefficient. It is a constant which depends on the wavelength or the species that is being analyzed. So normally Lambert-Beer's law can be used to determine the concentrations of different solutions. So if you have a certain solution and a certain solution of a compound, uh, you will know the value of this small a because small a is constant for a particular compound. And you will also know the path length because the compound is kept in some kind of sample holder. You know the length of the sample holder. So L is also known. So we can measure capital A. And since in the right hand side, we know this small a, we know L. So from capital A, we can find out the concentration. So from Lambert-Beer's law, concentration of an unknown solution can be determined. So now we will go into UV visible spectroscopy. So
how we will determine that absorbance? We have to measure it, na? We
yeah,
have
yeah.
to.
See, absorbance you will measure by this formula. So intensity of the initial light you can measure, and intensity of the final you can measure. So absorbance is a experimentally measured quantity.
Or ma'am, with the help of that, when we put the sample in the spectrophotometer, it gives the value of OD, and then from that we can measure the absorbance.
Yes, that also you can do. Yes, that is also another way.
And then we can find out the concentration.
Absolutely, correct, correct.
Okay, ma'am.
Okay, so now we will go into UV visible spectroscopy. So you know that any two orbitals can combine in two ways. So suppose there are two p orbitals here. There can be a sigma bond between the orbitals. So suppose the same phase of both orbitals are combining. So this side is also plus, this side is also plus. That will give a sigma orbital. And another is when they are in opposite phase, like shown here. Then you can see the interacting region will become small. That is the sigma star orbital. So any two orbitals will combine to give a sigma and sigma star orbital. This is in case of a head-on overlap, which is the sigma bond. If there is a side-by-side overlap, it will be the pi bond. Pi can also be pi and pi star. So if they are combining in the same phase up and same phase down, so then plus and plus, the intensity will increase, and minus intensity will increase. That is the pi. And if they are combining in opposite phase, they will kind of be repelled from each other. That will be the pi star orbital. So any sigma bond will have both sigma and sigma star, and pi bond will have pi and pi star. So there are many energy levels that are forming. The N is the non-bonding electrons. So whenever you have a lone pair of electrons, those are non-bonding electrons, and they will stay in the non-bonding orbital. Now, if you have a pi bond can form both pi and pi star. One bonding orbital, one anti-bonding. And sigma bond will form a sigma bonding and sigma star anti-bonding orbital. So these are the different electronic energy levels possible, and transition from one to another energy level will give you the electronic energy level transitions. Here, the most common transitions that are normally observed are the ones highlighted here, which is from N to pi star or from pi to pi star. These are the most common transitions observed in organic molecules, and the lambda is around 200 to 600 nanometer. So around UV to visible spectra. So whenever we have electronic spectroscopy, these are the transitions we are mainly talking about. One example is shown here. You have a carbonyl bond, C double bond O. So the single bond is the sigma bond from which you are getting the sigma and sigma star orbitals. The pi bond, from that you are getting pi and pi star. And the lone pair on oxygen are the non-bonded electrons, that is the N. So this compound C double bond O or the carbonyl group will have all these electronic levels, and the most common transitions which we will observe are these two, N to pi star and pi to pi star. Now this is
Ma'am, this in that diagram upper left, this HOMO and LUMO, what are these?
So HOMO means highest occupied molecular orbital. So suppose when you have a sigma bond, so there are two electrons involved in any bond, right? So in sigma bond, the two electrons will occupy the sigma orbital. In pi bond, two electrons will occupy the pi orbital. And non-bonding, you have, say, two electrons here. So when it is saying HOMO, so these two levels are empty. So in this particular molecule, this is your HOMO, which stands for highest occupied molecular orbital. And this is your LUMO, which is the lowest unoccupied molecular orbital. So HOMO, if you have only one sigma bond, then you won't have all this pi orbital. So imagine you have only one sigma bond, then you don't have any of these levels. You only have two levels, bonding and anti-bonding. In this case, that this will be the HOMO, this will be the LUMO. So I'll just discard these. HOMO basically stands for highest occupied molecular orbital and LUMO for lowest unoccupied molecular orbital. So if you have a single sigma bond, the HOMO will be sigma and LUMO will be sigma star. If you have a pi orbital, so imagine this compound, but imagine you don't have the non-bonding orbital. So this energy level you don't have. Then your pi will be HOMO, pi star will be LUMO.
Ma'am, is there any high unoccupied molecular orbital, or these two cases are only possible?
These two cases are possible. There is one more case called SOMO, which is singly occupied molecular orbital. But that is a comparatively rare case, which we don't need to look at right now. So these two cases are only possible.
And in the right diagram, that blue color
Yes.
electrons, that is sigma bonded or pi bonded?
This is
Pi
pi
bonded.
because it is like pi bond is you have in upper and lower with the nodal plane in between. Sigma bond will be present like this. Sigma bond will be present like this.
Mm-hmm. Ma'am, so here there is no sigma bond.
Actually, sigma bond is also there. It is not shown because you cannot have pi bond without sigma bond, right?
Mm-hmm.
Whenever you have double bond, one of these is sigma, one is pi. You cannot have only pi bond. Here sigma is not shown for just to because they're emphasizing on the pi bond.
So ma'am, CO, in case of CO, one is sigma and one is pi. Here that black line
Correct.
is sigma and that is pi.
Correct.
So ma'am, what this
Yes.
picture is depicting about means?
It is just showing the different orbitals, that this is the unoccupied orbital, and it is not depicting anything as such. It is just here the different energy levels are shown, and this is just explaining the different bonds that are caused by these energy levels.
Okay.
Do you have a doubt?
Ma'am, that HOMO and LUMO now also means that this portion of bonding and anti-bonding, what will happen and what will be when these cases like N bonding to pi star, why these are only favorable and rest are not
See,
favorable?
one reason for that is that energy difference, you can see these two energy difference is the minimum. So there is something called probability of transition. As the delta E increases, energy difference between two states increases, probability of transition becomes very low. So these other transitions are also possible, but they are very low probability. So the intensity is low. But these two, N to pi star and pi to pi star, you can see the energy difference is comparatively lowered. And so these two probability of transition is very high. And so these are the two most intense peaks that we see.
But from non-bonding to sigma star, that is anti-bonding, the probability there also in that case also is less.
Uh,
And to sigma star.
Comparatively sigma, see, whenever you sigma bond is stronger than pi bond, right? So sigma anti-bonding will be high and sigma bonding will be low. So 1 second, there is some problem in, yeah. Uh, yeah, so as I was saying, sigma star anti-bonding is actually much higher, like if you see the energy difference, maybe I'll make another slide. I will put the delta E and the probability of transition. I'll put that table properly. Then you can probably understand is that, see this, when I'm saying these are the most common transitions, this is from experimental results. It was observed that these two have the highest intensity. So maybe here I understand, looking at from here, it appears that N2 sigma star is also similar energy, but actually if you see the values, it is much higher energy.
Like that N2 sigma bonding is also may also take similar energy. Mm,
Huh, huh.
Means both are same only, but I think due to experimental, after experiments we give the results, we give the
Huh,
explanation.
huh.
So
Exactly, exactly. That is, like people see from experiment and then they try
hmm,
to give some explanation. So yeah,
yes,
you are absolutely correct.
okay.
One second. So, how is UV visible spectroscopy used in case of biological molecules? So, basically, proteins, you know, the aromatic amino acids, which are phenylalanine, tyrosine, and tryptophan. Whenever a protein has one or more of these aromatic amino acids, they will have absorbance maxima at around 280 nanometer.
Excuse
So,
me,
these
ma'am.
are, haha,
Ma'am, sorry, I am disturbing you in between. Ma'am, that
haha,
one graph was there na, in the previous slide, means previous to previous slide. That one black.
this one.
No, ma'am. Yes, ma'am. This one. This one. I need some explanation regarding this. What is happening in this? And what is
So
that black line?
yeah, so here we are plotting absorbance versus concentrate. So in this, so there are three compounds here. Uh, Imagine these three colors as three compounds, and here we are plotting absorbance, which is an experimentally determined quantity in the y-axis, and in the x-axis we are plotting the concentration. And we want to find out this epsilon, that is the absorptivity. So we will plot absorbance versus concentration, and we already know the length. So from the slope of this graph, we will get the slope of this graph will basically be equal to epsilon L, and we know L, so we can find out epsilon from this graph. So this graph is just showing how epsilon can be calculated for different compounds.
What is this epsilon?
Epsilon
Slope.
is this A, which is the molar
Okay.
absorptivity. I was saying, no, every
Mhm.
compound has a specific value of molar absorptivity,
Yes, ma'am.
but
Yes,
how
ma'am.
can we calculate that? It is by plotting absorbance versus concentration.
But how we will calculate the absorbance by OD measurement only in this case? Because
Ha
we don't know this absorbability also, then we can't calculate.
absolutely. It has to be done only by OD.
And then we will plot the graph, and then we will calculate the absorbability.
From the slope, we will get absorbance in absorptivity into length, and length we know, so we will be able to calculate the epsilon.
Pardon, ma'am.
So we will change the different concentration, and we will get absorbance value from the OD at different concentrations. Then we can draw a straight line, and the slope of that straight line will be this product, which is A into L, and we know the L, so we can calculate the A.
So, ma'am, by the slope means which we take na the equation y equals to mx plus c. By that we can't calculate this slope.
That is the same equation, no? One second. See, here intercept is 0. Imagine y is capital A. There is no mx plus c. It is just y equal to mx. So x is your concentration, y is your absorbance. So the m, that is the slope,
Mhm.
is your A into L. That is what I'm saying. So slope of this straight line will be A into L, and we know L, so we can calculate this small a.
Okay, ma'am. Okay. Got it.
Intercept is 0. You can see intercept
Yes,
of
ma'am.
all three
Yes, ma'am.
lines.
Intercept is 0.
Huh, huh. Yeah. So I was saying that proteins, they have, whenever proteins have any one of these three aromatic amino acids, they will show very characteristic absorbance peak at around 280 nanometer, little bit shifted from 280 also. And the most intense peak you can see is for tryptophan. So whenever, suppose you have a protein which we want to detect by absorbance, sometimes something called a tryptophan tagging is done, where an additional tryptophan is added to one end of the protein so that we can study it using this UV visible spectroscopy. So 280 nanometer plus minus X is the wavelength range around which this peak will appear for the aromatic amino acid, and 260 nanometer is the peak which appears for the nucleic acids. So there is a certain formula which has been derived again from different experimental results to calculate the concentration of a protein in an unknown solution. So the absorbance at 280 nanometer is taken and multiplied with 1.55, and the absorbance at 260 nanometer is taken and multiplied with 0.76. Then they are subtracted to find the concentration of a protein in mg per ml. So basically in a cell you have both nucleic acid and protein. So the protein will absorb at 280 nanometer and nucleic acid will absorb at 260 nanometer. So how this formula has been derived, I also don't know, but they have seen that from this formula, if you have a cell and you are doing the, you're passing light through the cell and you are seeing the absorbance, if you put the absorbance at these two wavelengths and subtract them, you will get the concentration of the protein in mg per ml. So, and for a protein to be visible by UV visible spectroscopy, it must have one or more of these aromatic amino acids. And since tryptophan has the highest intensity, generally tryptophan is preferred. So proteins lacking these amino acids cannot be measured using UV visible spectroscopy.
So, if a sample is provided, and so the sample should contain all these three: phenylalanine, tyrosine, and tryptophan.
Any
These
one is
three.
also fine because these three will show peaks. So it can either have any one or it can have all three. It does not matter. But it must have at least one.
But ma'am, the sample might also contain all the amino acids, rest of the amino acids
Huh.
present there.
Then it
So,
cannot be studied using UV visible spectroscopy. Either you have to do a tryptophan tagging where you add an additional tryptophan to the end of the protein, or you have to study it by some other spectroscopy like fluorescence spectroscopy or something.
so spectrophotometer, in the case of spectrophotometer, that spectrophotometer is also UV visible spectrophotometer.
No,
So
no. This, okay, you say what you're saying.
so in that case, so we can measure everything. We can measure the absorbance, sorry, OD of the given sample, whether it is a protein or I think a protein or that nucleotide. I don't know about nucleotide, but protein we can measure. So
Huh.
in that case, hmm.
Right now we are only talking about UV visible spectroscopy, but if you have a spectrometer, see, other amino acids will also absorb light at different wavelengths, but it will not be in the UV visible region. That is why if you are studying it by a spectrophotometer which has a wavelength range only within the UV visible spectrometer, UV visible range, then it has to have one of these three amino acids. Otherwise, in a general spectrophotometer where you are putting light of all the wavelength ranges, you can study any protein, because as you will see later, different kinds of the amide bond itself will absorb light at a certain wavelength. So using spectrophotometer you can study any protein, but if you have a UV visible spectrometer where only wavelength of UV visible range is passed through it, then you can only study the protein if it has one of these three amino acids.
So why is that always means this due to their aromaticity this
Yeah,
is
yeah, due to
happening?
the aromaticity. So we are not going that much into detail, but what happens is that whenever there is an aromatic ring, this energy difference is very low, because again, I can include that later, but these transitions are very much favorable whenever you have any aromatic system. So that is why, because of the aromatic ring, these three are preferred.
So, ma'am, in this case, can we measure the DNA structure? Purine and pyrimidines, they also have aromaticity.
They will also show up in, that is what this is saying, no, that nucleic acids will
Yes, ma'am.
show
Yes,
a peak
ma'am.
around 260 nanometers. So yeah, nucleic acids will also show up in the UV visible spectrophotometer.
Okay, ma'am.
Now we'll briefly go into circular dichroism, or CD. So light can be unpolarized. That is, it is there is like it is in different directions. When it passes through a polarizer, suppose you have so a polarizer is blocking light of most of the directions and allowing only light of one direction to pass through it. So this is called plane polarized light, where only light in one plane is being allowed to pass through it. In case of circular dichroism, what happens is that, so you can see this is a linear polarized light, the first example, where you are only allowing light in this plane to pass through it. In circular polarization, what happens is that light in two perpendicular plane is allowed to pass through. One is this plane, another is the plane perpendicular to it, going like this. So these two lights, they kind of interact and combine with each other to give this kind of a circular polarized light. So circular polarized light, if you imagine this as the x-axis and this has the y-axis, circular polarized light will have the same magnitude in x and y-axis. That is why it is circle. And elliptically polarized light is that when suppose here y magnitude is greater than x magnitude, so then it is not a perfect circle, it becomes like a elongated circle, which is also called a ellipse. So that is the elliptically polarized light. So this circularly polarized light can be of two kinds. One can be left-handed, which this is the example of the left-handed, which is like anti-clockwise direction. So if you start from here, you follow the light, you can see it is anti-clockwise. Another is the right-handed, where if I'm starting from here, it is following the clockwise motion. So in circular dichroism, uh, light of both these kinds, left-handed circularly polarized and right-handed circularly polarized light, is passed through the sample. And depending on the nature of the sample, it will absorb in a different way. So here it is shown in a schematic way. This red line is the right-handed circularly polarized light in the clockwise direction. And the green line is the left-handed circularly polarized light in the anti-clockwise direction. Initially, both have equal components. You can see half of the circle is red, half is green. When it passes through the sample, sample will preferentially absorb this particular sample is preferentially absorbing the right-handed polarized light. So the red is being absorbed, and so the magnitude of red is decreasing and magnitude of the green is increasing. So initially, the difference between left and right was 0 because both was there in equal magnitude. After passing through the optically active sample, if you again take the difference between left and right, it will give a certain value, and that is basically what causes the signal in CD spectroscopy. So what you are measuring in CD spectroscopy is the difference in absorbance. So AR is the absorbance of the right circularly polarized light. AL is the absorbance of the left circularly polarized light. So the difference in absorbance of these two is what you are measuring in CD. You can write absorbance as epsilon CL. Epsilon is the absorptivity, C and L is the concentration and length by Lambert-Beer's law. You can take the concentration and length common because the sample has one concentration and the path length is also same. So the difference in the absorptivity of the right and left polarized lights in the bracket multiplied by LC. So delta A is delta epsilon LC. This is what you are measuring in the circular dichroism. This is what is plotted in the y-axis, and you have wavelength in the x-axis. Now, circular dichroism is mainly used to understand the secondary structure of proteins. So, different secondary structures will have very characteristic spectra. So, if you have an alpha helix shown by the blue here, it will have one positive band in 193 nanometer and two negative bands around 208 and 222 nanometer. So whenever you see this kind of a signal, you can say the protein is adopting alpha helix conformation. Beta sheet, it will have again two different characteristic bands. This orange line is the beta sheet. Similar to the alpha helix, it has a positive around 195, but only one negative around 218. And random coil will have only one negative at around 195. So you can see different secondary structures like alpha helix, beta sheet, beta turn. They will have positive and negative bands at different values. And this is like the signature of that particular secondary structure. So if you are given a random circular dichroism spectra, you can look at that spectra and predict that what secondary structure it is adopting. So again, you don't need to understand the details of how it is happening too much. You just remember this, that in circular dichroism, first the light is circularly polarized. That is, two light rays are allowed to pass in which are in perpendicular direction. One is in x direction, one is in y direction, and initially the magnitude is equal. After passing through the sample, the magnitude becomes different because the sample is absorbing the right and the left polarized light to different extents. When the magnitude becomes different, you are calculating the difference in this magnitude between the right and the left circularly polarized light, and the difference is being plotted in the y-axis. Each secondary structure will have a very characteristic circular dichroism spectra, and depending on the circular dichroism spectra, you can predict the secondary structure. So you can remember these three, the alpha helix, beta sheet, random coil. These three you can remember because these are very characteristic secondary spectra. Now you can see how circular dichroism spectra changes with temperature. So at 0 degrees Celsius, this blue line, you can see it is characteristic of alpha helix. Now, as you are increasing the temperature at 75 degrees Celsius, the spectra is like the random coil spectra. In random coil, there was only one minima at 195 nanometer. Here, if you extend the spectra, it is not showing the whole spectra, but the spectra will come like this. So, at 0 degrees Celsius, it was alpha helical. At 75 degrees Celsius, it is becoming random coil. So at high temperatures, the alpha helix is dissociating into a random coil orientation. Similarly, you can see here different proteins are shown. So this black line, it is characteristic of alpha helical. That means this protein, mostly the secondary structure will be alpha helix. So this protein is myoglobin, which you can see is mostly alpha helix. Then this green, then there can be some proteins which will not be fully alpha helix, not be fully beta sheet. So some kind of mixture is there. You can see this red line lysozyme. It has some characteristic of alpha helix because you have one maxima around 193 and two minima here. But the two minima are very small. So the structure is not purely alpha helix, but it is not purely beta sheet also. So there is a mixture of alpha helix and beta sheet that is making up this protein, and the CD spectra that you are observing is because of this mixture. So in that case, you will not get the characteristic spectra of either alpha helix or beta sheet. You will get a spectra somewhere in between both the structures. In order to calculate how much alpha helix, how much beta sheet is there, there are different fitting softwares. So imagine your net CD that you are observing, the theta is what we are plotting in the y-axis, which is the ellipticity. So this is the total theta. There is some contribution from alpha helical structure, which is the first term, some contribution from beta sheet structure, second term, and some contribution from the random coil structure, that is the third term. So imagine a protein where you have alpha helix, imagine this protein, and you have some alpha helix, some beta sheet, some random coil. You don't know how much contribution of each. Then there are certain softwares which can predict that. So one of these softwares which are very freely available is BestCell. I'll demonstrate that later. So the software, if you enter the CD spectra in the software will predict that how much when the CD spectra of this protein was inserted in the software, it predicted that there is 80% alpha helix and 20% random coil. There is 0% beta sheet. And when the X-ray crystallographic structure was compared, it was very close to the predicted value. It was seen that 78% helix was there and 22% coil. So from the CD spectra, just by looking at the spectra, you can predict that this is the secondary structure. If it is, suppose a protein is only alpha helix, then it is very easy to predict that this is an alpha helical protein because you will see this blue signal. But if a protein has different amounts of helix, beta sheet, and coil, then it is difficult to predict. Like this red spectra, you cannot properly predict whether this is beta sheet or alpha helix or what it is. So in that case, you have to insert the spectra in one of the prediction softwares, and the software will give you an idea about the contribution of each of the different secondary structures. Here, so some of the basic softwares, they only consider 3 secondary structures: alpha helix, beta sheet, and random coil. But as the softwares have improved, they also consider other secondary structures like beta turn, and they can also differentiate between parallel and anti-parallel beta sheet, and so on. So from the circular dichroism, using software, now you can even predict that how much percentage secondary structure makes up the protein. Now, there is a compound called trifluoroethanol, which induces helicity in peptides. So imagine you have a peptide. Yes.
Ma'am, that in that graph portion, we have to put the whole sample in where we have, how we will do that thing. How we will do the
This software you are talking about?
Yes, ma'am.
So see, you have an unknown protein which you don't know the secondary structure. You do the circular dichroism experiment and you will get this graph. Now the X and Y coordinates of this graph can be inserted in the software. So basically the graph has Y coordinates, that is this ellipticity, and X coordinate, the wavelength. You can insert it into the software and the software will predict how much percentage of each secondary structure is there.
Okay, ma'am.
Now there is a molecule called trifluoroethanol. So basically, if you take a peptide in water, you can see the peptide has NH bond, C double bond O bond. The water will solvate these bonds and the peptide will be unfolded. But one special characteristic of this trifluoroethanol molecule is that it very nicely inserts itself in the helical structure and it stabilizes the helical structure. So suppose you have a helix, which in water it is unfolding and becoming random coil, because helix is stabilized by hydrogen bonding interactions. But in water, the water will interfere with the hydrogen bonding interactions and unfold the helical structure. But trifluoroethanol is a molecule that promotes the helical structure by stabilizing the intramolecular hydrogen bonds in the helix. So if you use trifluoroethanol, the helicity will increase. You can see from this blue to the red line, in the blue line is in water. It is still helical, but so the lower you go in the graph, the more the percentage helicity is increasing. So there is a certain equation to calculate percentage helicity. We are not going into that. Basically, you can just remember that characteristic peaks of helix is 208 and 222. Now, lower these peaks are, more helical the molecule is. So you can see peak here also 208, 222. And in trifluoroethanol also these peaks are there, but the intensity of the peak is more. That is, it is lower. So the compound is becoming more alpha helical in trifluoroethanol. Sometimes what happens is that you can see here the intensity is same, but there is a shift. Basically, trifluoroethanol will stabilize the helical structure of the molecule. So, but there are certain limitations. So we can use CD to predict the secondary structure, but there are certain limitations. One is that from the CD spectra, these prediction softwares, when the protein is made up of only like 3 to 4 secondary structures, the prediction softwares are very accurate. But when the protein is made up of, say, 10 to 11 different kinds of secondary structures. So, in beta turn also you can have type 1, type 2, type 3, so on. So suppose the protein has many different kinds of beta turns, parallel beta sheet, anti-parallel beta sheet, then the prediction software begins to fail, and then it does not give a very good prediction. And another problem is that the CD spectra often depends on tertiary structure as well. So far we have only seen proteins which have very well defined secondary structure. This is clearly helix. This green lines are clearly sheet. But sometimes in globular proteins, the folding happens in such a way that the secondary structure cannot be differentiated very nicely, and it is the tertiary structure that determines the CD spectra. In those cases also, the prediction becomes very difficult. So these are some limitations of the CD spectra in determining the structure of the protein. Now we will look at some other processes that can happen whenever there is light absorption. So absorption, you know that absorption. So you know that absorption can happen from a lower energy state to a upper energy state. And when it comes down from the upper energy to the lower energy state, that is the emission, also called as fluorescence. So absorption and emission generally happen between states having the same spin property. So as singlet state, or S, is when you have two electrons in opposite spin. So the net spin is 0. Even in this excited S1 state, you can see the two electrons are in opposite spin. So the net spin is 0. So any state where the net spin is 0 is called a singlet state defined by S. And absorption or emission within that state is like a very favorable process. And that kind of emission from one singlet excited state to the singlet ground state is called fluorescence. Now, suppose you have, there is also something called a triplet state where you have the two electrons in the same spin. So suppose from the singlet state, the electron comes to the triplet state. And from the triplet, it will relax to the ground state. Then this red line, which is from triplet excited state to ground state, that is called phosphorescence. And that is another kind of phenomena that can happen. So in any spectroscopy, fluorescence, these are basically defining the different kinds of spectroscopy. Fluorescence spectroscopy is when from a singlet excited state, the molecule comes down to singlet ground state. Phosphorescence spectroscopy is when you have triplet excited state and the molecule is coming down to singlet ground state. So these are just defining the different kinds of absorption and emission that can happen. Now, so let us first look at this absorbance and fluorescence. Normally, when you go from a singlet ground state to a singlet excited state, that is absorption. Now, before emission can happen, a certain energy loss happens because this S0 and S1 are the electronic energy levels, and these smaller energy levels are the vibrational energy levels. So after a molecule has absorbed energy, it can lose some energy by vibration, and then fluorescence will happen. So the energy emitted in fluorescence is always lower than the energy absorbed because there is some energy loss that happens in the vibrational energy levels. So this difference in energy, that is the difference in wavelength, is called a Stokes shift. So this fluorescence is lower energy, that is higher wavelength. So this red peak is the fluorescence peak, and absorbance is higher energy, that is lower wavelength. So this black peak is the absorbance peak. The difference in wavelength between these two is called the Stokes shift. So if you know the wavelength of absorbance and the wavelength of fluorescence, you can subtract them to find this Stokes shift. There is a term known as quantum yield, which is defined as the ratio of the number of photons emitted by the number of photons absorbed. So if the quantum yield is high, that is, then this energy loss here will be low because the ratio of emission by absorption is high. So if you have a compound with a high quantum yield, that means it will show very nice fluorescence. And if the quantum yield is low, that is number of photons absorbed is high, but emitted is low, then the fluorescence will also be low. And there is another term that is defined, which is called the life. Are you saying something?
Ma'am, in case of quantum yield, the number of photons emitted will always be less than the number of photons absorbed.
It is always less than 1. But quantum yield, say greater than 0.8, is considered a good quantum yield. But it will always be less than 1. It can never be greater than 1.
Okay, ma'am.
There is another term called the lifetime of the excited state, and that is defined by 1 by epsilon plus KNR. So basically, you can the relaxation can happen either by non-radiative processes, that is, suppose from one vibrational level it is coming down to the lower vibrational levels, these red arrows, these are called non-radiative processes. They are defined by this KNR term. And then you can have fluorescence where it is coming down from S1 to S0, and it is giving rise to a wavelength here, say of h nu. This is called radiative process, that is defined by this term. So you know that in any like kinetics, you know that 1 by rate constant is the lifetime in any kinetic experiment. So here there are two rate constants. One is the non-radiative processes, that is these vibrational relaxation, and one is the radiative process, that is this fluorescence. So 1 divided by both these rate constants gives you the lifetime of the excited state, because the relaxation from the excited state can happen by both the non-radiative process and the radiative process. So again, this is just a term that is being defined. So this we have already seen emission spectra and absorption spectra, and we have seen the difference between these two is the Stokes shift. There are certain other terms which are being defined here. So suppose you can see wavelength of the emission spectra is greater than the wavelength of the excitation spectra. So there is a wavelength shift in this direction. That is called a bathochromic or red shift. If there is a wavelength shift happening in the opposite direction, that is called a hypsochromic or blue shift. And if the intensity is increasing, it is called a hyperchromic shift. If the intensity is decreasing, it is called a hypochromic shift. These are just different terms that you can remember. Yeah, it is just defining the different terms. So now we will look at the solvent effects. So basically, when you have so if you remember, S1 is the excited state. Now, in a less polar solvent, the stabilization S1 energy decreases, but if you have a more polar solvent, S1 energy will decrease even more. So, as you are, we are looking at S1 to S0 transition. Suppose we are doing it in a less polar solvent. So S1 energy becomes down to this green level. So now this is the emission energy. Or if you have a more polar solvent, stabilization will be even more. So this delta E will be lowered. So the delta E is lowered for more polar solvent. So delta E lowered means lambda is higher. So as you go from a non-polar solvent like heptane to a polar solvent like water, you can see the wavelength of absorbance is increasing. So suppose we are starting with 100% heptane. At that time, the wavelength was around 400. Then we are slowly decreasing the amount of heptane, say 90% heptane, 10% water, 80% heptane, 20% water, until we go to 100% water, and we can see the wavelength has come around 525. So the wavelength has increased as we just changed the solvent from a non-polar to a polar solvent. And why this is happening is because as the polarity of solvent increases, the excited state becomes more and more stabilized. And if the excited state is stabilized, then the energy difference between excited and ground state reduces. That is, the wavelength increases. So as we are going from 100% heptane to 100% water, this wavelength of absorbance is increasing from around 400 to 525. So the shift is happening in the right side, from low to high wavelength, and that kind of shift is called a bathochromic or red shift, where we go from low wavelength value to high wavelength value. So that is the solvent effect on this kind of spectroscopy. There is also something called fluorescence quenching. So basically, if you have, so quenching happens when the intensity of fluorescence decreases. So we will define each one by one. So there is something called collisional or dynamic quenching. So suppose you have an excited fluorophore, which is supposed to emit a certain wavelength as fluorescence, but that is colliding with another molecule or atom. So this molecule, naphthalene has a certain fluorescence intensity. But suppose there is some other impurity in the solution. Impurity like this can be oxygen or iodide or acrylamide. These are molecules which will collide with the fluorophore, and the energy will be transferred to this molecule. So the energy is being transferred to the quenching molecule, and so fluorescence does not happen, or the intensity of fluorescence decreases. Basically, fluorescence was happening due to this energy transfer. But suppose 50% of this energy is being transferred to the colliding molecule, which is called the quencher. So if 50% of the energy is being transferred to this quencher molecule, then the intensity of the fluorescence will decrease. So this kind of phenomena is called collisional or dynamic quenching, where the intensity of fluorescence is decreasing because of collision with some other molecule called a quencher, to which some energy is getting transferred. So there is an equation which defines this, which is called the Stern-Volmer equation. So F0 is the fluorescence intensity in absence of the quencher, and F is the fluorescence intensity when quencher is present. So F is always less than F0. So F0 by F is greater than 1. This is defined as 1 plus a constant Ksv into the concentration of the quencher. So as we increase the concentration of the quencher, that is the concentration of this molecule, more and more energy will be transferred to this molecule. So this term will be greater. The right hand side term will become greater as we increase the concentration of the quencher. That means F0 by F will become greater. That is, F will become lesser. Because more the amount of quencher is there, less will be the fluorescence intensity. So that is the Stern-Volmer equation, which is saying that as we increase the concentration of the quencher, the intensity of fluorescence will decrease because more energy is getting transferred to the quencher. So the net fluorescence intensity will decrease. So that is the Stern-Volmer equation. And F0 by F can also be written as tau 0 by tau, where so F0 is the fluorescence intensity when there is no quencher present, and F is the fluorescence intensity in the presence of the quencher. We can also write this in terms of lifetime. So tau 0 is the lifetime in absence of quencher, tau is the lifetime in presence of quencher. So we can write, instead of F0 by F, we can write tau 0 by tau is 1 plus, instead of Ksv, we can write Kq tau 0, where tau 0 is the lifetime in absence of quencher, and Kq is the is the rate constant. So there is a rate constant that is, so from F, the fluorescent molecule, energy is getting transferred to the quenching molecule whenever there is a collision happening. So the rate constant of this collision is defined by this Kq term. Again, we don't need to go into how from this equation is coming. We don't need to go into that. You can just, so the first equation is pretty clear. As we are increasing the concentration of the quencher, the fluorescence intensity is decreasing. And the second equation also, instead of this constant Ksv, we are writing it out in terms of the rate constant of collision and the lifetime. So you can just remember that from the first equation, the second equation is coming. We are not going into the derivation of this. And another kind of, so in this, how the quenching was happening, the two molecules was colliding. Some energy is getting transferred from the fluorophore to the quencher, and the fluorescence intensity is decreasing. Another way in which the fluorescence intensity can decrease is that if a complex is forming. So the fluorophore and the quencher are coming together, they are forming a complex, and in that complex, the quenching is happening. So the previous one, just 1 second. So the previous one was a case where it was just colliding and energy was getting transferred. In this case, so that is why it is called a dynamic quenching, because the molecules are moving and colliding with each other. This is a static quenching because the molecules are coming together, forming a complex. In that complex, the energy transfer is happening. And because energy is getting transferred to the quencher, the fluorescence intensity is decreasing. So that is called static quenching, where because the molecules are forming a complex. So that is about quenching. There is another phenomena called FRET, that is fluorescence resonance energy transfer. So suppose you have a donor molecule.
Ma'am.
So, yes.
So in the previous slide, that calculation portion, this Ka is the same.
Ka, yeah. So you have here Ksv was the constant, which is the rate constant of this collision. And here, instead of Ksv, you have Ka, where Ka is this association constant. And if you have a molecule where both static and dynamic quenching is happening, then the two terms are just multiplied. So 1 plus Ksvq is multiplied by 1 plus Kaq. So that is if both static and dynamic quenching are happening.
Ma'am, and in the case of dynamic quenching, the lifetime will get reduced.
Yeah, lifetime of excited state is reduced because you are transferring some energy to the quencher. So lifetime will get reduced.
Ma'am, but in the case of static quenching, the lifetime is not getting reduced.
No, lifetime will get reduced in both the lifetime of the fluorescent state will get reduced in both the cases, right? Because fluorescence, this suppose the excited state is this F star. If no
Yes, ma'am,
quenching
but
was
I got that point. But about the lifetime of sample, it's written in the third point that lifetime of the sample will not reduce. Third point, ma'am.
it is saying the fluorescence of the sample is reduced since the quencher is reducing the number of fluorophores which can emit. So I am not sure. Where are you seeing lifetime?
Ma'am,
Sorry.
third point.
This one. Oh,
Sorry, ma'am. Second point. Sorry, second point.
Okay.
Yes, ma'am.
Static quenching will not reduce the lifetime of the sample since those fluorophores which are, yes, which are, in dynamic quenching, what is saying is that in static quenching, there is an equilibrium you can see here that some of the fluorophores will form the complex, some will not form the complex. So the one which is not forming the complex, they will still have the same lifetime. But in
But
dynamic
those that
quenching,
will form,
those where the complex is forming, there the lifetime will be reduced. So I guess I also have to look more into this second point because what it is saying is that when complex, say 50% of the molecule is forming complex, then in 50% of the molecule, there will be a reduction in lifetime, and in 50% you will have the same lifetime.
okay.
That is what it is saying basically.
Okay.
So there is another phenomena called Forster's resonance energy transfer. So suppose you have one molecule which is you're exciting the electron in the donor molecule and it is emitting something. Now, instead of this emitted ray is getting absorbed by another second molecule, which is the acceptor molecule, and that is getting excited. So here there are two molecules. One is the donor. So the donor is initially getting excited and the energy from the donor is getting transferred to the acceptor. And the acceptor is getting excited. And when the acceptor is coming back to ground state, this is the net energy that we see. So this entire process is called resonance energy transfer because energy is getting transferred from donor to acceptor. And it is very much dependent on the distance between the donor and acceptor. So if this distance is less than equal to 10 nanometer, this kind of phenomena can be observed. There is a so it is kind of dependent on 1 by r to the power minus 6. You don't need to remember the formula. You can just remember that with the increase in distance, this efficiency of transfer is reducing. And if the distance is less than equal to 10 nanometer, this can happen. Otherwise, this will not happen. And also, if the donor and acceptor are at 90-degree angle, then this kind of transfer cannot happen. So this is a process where normally you have one molecule which is absorbing and that molecule only is doing the fluorescence. Here there is a transfer from the donor to the acceptor. Acceptor is again getting excited, and when the acceptor is coming down to ground state, that is the photon that we observe. So this is kind of an energy transfer. So again, like we saw that in UV visible spectroscopy, we have the three aromatic amino acids, phenylalanine, tyrosine, and tryptophan. Similarly, for the fluorescence spectroscopy, these three amino acids show very nice fluorescence. So absorption and fluorescence are connected, right? So these three show good absorption means these three will show good fluorescence also. So that is what this is saying, is that they have very characteristic values for the of wavelength at which they are showing fluorescence. So if the proteins have one or more of these aromatic amino acids, they will show up very nicely in the fluorescence spectroscope. And there is a protein called green fluorescent protein, which has this kind, three amino acids, which are basically serine, tyrosine, glycine. So this serine, tyrosine, glycine amino acids, they form a kind of autocyclization. This kind of a cyclic molecule is formed. And you can see this has alternating single and double bonds, double, single, and so on. And when you have a system with alternating single and double bonds, it shows very nice fluorescence. So this green fluorescent protein is a characteristic protein which shows very nice green color fluorescence. And it shows this fluorescence because of these three amino acids. These three amino acids, serine, tyrosine, and glycine, they form a cyclic moiety like this. And in this cyclic moiety, you can see that, so tyrosine itself will show fluorescence. But when this kind of a cyclic molecule is formed, the tyrosine system, so tyrosine was double, one benzene ring. When this cyclic molecule forms, the aromatic system is extended. So along with the benzene ring, you have another single, double, single, so on. So when you have alternating single and double bonds like this, the fluorescence becomes even more effective. So this is the chromophore that is resulting in the green fluorescence, in the green fluorescent protein. And you can remember that there can be certain mutations, like instead of the serine, if you have threonine, so then the fluorescence is enhanced even more. And this is called enhanced green fluorescent protein, or EGFP. So this is the green fluorescent protein, that is GFP. And instead of the serine, if the serine is mutated to a threonine, then the fluorescent intensity is even higher. Now, why that is higher, we don't need to go into that. You can just remember it, that this trio of amino acids, serine, tyrosine, glycine, leads to very nice green color fluorescence. And if you mutate the serine to a threonine, the fluorescence intensity is enhanced. So green fluorescent protein, GFP, becomes EGFP, that is enhanced green fluorescent protein. So IR spectroscopy is basically about bond vibrations. And so the vibrations can be stretching vibrations. So the two bonds are stretching symmetrically. They are both stretching in the same direction, or they are stretching in opposite directions. They can be bending vibrations. So the two bonds are coming close together. So imagine this is a scissors. You are closing and opening the scissors. That is a scissoring motion. And there are different kinds of other vibrations also. All these vibrations can be studied using the IR spectroscopy. So in any chemical sample, there are characteristic peaks in the IR spectroscopy for characteristic functional groups. So you can have bands which are weak. So they will be small bands like this. If the absorbance is high, they will be medium or strong bands. And each functional group will have a characteristic band. So you can see in this graph, it is showing that which functional group appears around which range. So the carbonyl functional group is appearing around 1650 to 1800. OH is coming around 3200 to 3400. So depending on the peaks that are observed, we can predict which are the functional groups present in our molecule. And so you can see here, this is an aldehyde. Aldehyde will have C double bond O stretch and CH stretch. Ketone will have only C double bond O stretch, because there is this sp2CH is not present in the ketone. And the carboxylic acid will have C double bond O, but it will also have OH. So depending on the different peaks that are there, we can predict that what functional group is present in our molecule. Then you have the different amines. So NH stretching occurs at a characteristic range of around 3200 to 3600. So if you have NH2, you have two peaks here. But in this compound, you have only NH, so there is only one peak. Similarly, amide, if you have CONH2, that is primary amide, you will see two peaks like this. But in secondary amide, there will be only one peak of the NH because there is one NH. So again, it is easy and possible to differentiate between primary and secondary amides using that. If you just remember this chart, that which group is appearing around which range. So different solvents will also appear, have different characteristic spectra. So if you have a unknown sample, you can compare it with the IR spectra of a known sample, and you can predict that the unknown sample is, say, benzene here. So IR spectra is like the fingerprint of that particular compound. FTIR is basically, IR spectroscopy is the concept. FTIR is basically, it refers to the instrument that you are using. So FT stands for Fourier transform. Basically, what it does is that using the computer, it is converted to the spectra that we know. This is the spectra that we know. But originally, the spectra that is obtained is kind of like you cannot look at it and understand this is the spectra of the compound. This is processed through the computer to get the spectra that we know as the IR spectra. So FTIR basically just refers to the instrumentation. We don't have to worry about that. So FTIR spectra gives us information about the secondaries. So like you saw in CD spectra, you can put it in a software and it will predict that how much of each secondary structure is there. That can be done in FTIR also. So FTIR, you can look, this is the peak that was obtained, this outer envelope. And after putting it through the software has deconvoluted the peak. It has predicted that how much is responsible, like alpha helix is responsible for this much, turn is responsible for this much. So using a software, so putting the FTIR spectra through a software, we can predict that how much of each secondary structure is present. And there is some, the final thing that we'll discuss, just 1 second. So we have seen UV visible fluorescence FTIR spectroscopy. There is also Raman spectroscopy. Basically, what is Raman spectroscopy is that what we are, suppose absorbance energy and the released energy is the same, then it is called Rayleigh scattering. So far we were looking at transition between different energy levels. In scattering, that does not happen. Scattering, if you remember in the first slide, scattering is when the electromagnetic ray is hitting the molecule and just getting scattered in different regions. So that is called Raman scattering. And so that is why it is called virtual energy level. That means it is not transition between two energy levels. The lower energy level belongs to the compound. But in the higher energy level, it is not actually an energy level because it is kind of like, you can imagine it as the wavelength is hitting the molecule and getting scattered in different directions. Now, if the wavelength, like the initial wavelength energy is higher and final energy is lower, this basically forms Raman scattering, where you can so if in a scattering phenomena, if the energy absorbed and emitted are equal, then it is called Rayleigh scattering. And if the energy absorbed and the energy emitted are different, then it is called Raman scattering. So you can just remember this, that in Rayleigh scattering, the lambda of the excited thing, that is the laser, lambda laser and lambda scattering is equal. You can see the wavelength that is hitting it and the wavelength that is scattering, equal wavelength. If the wavelength hitting and the wavelength scattering are different, it is Raman. And there can be two kinds of Raman. One in which the scattering wavelength is greater than the hitting wavelength, that is called Stokes Raman scattering. Another in which the scattering wavelength is lesser than the hitting wavelength, that is the anti-Stokes Raman scattering. So again, we don't need to go into the details of Raman scattering too much. You can just remember this, that infrared spectroscopy we observe when there is a change in the dipole moment. So if the molecule is in equilibrium structure, we will not see any activity. But if the molecule is stretching in different directions, so if there is a symmetrical stretching, that means dipole moment is not changing because it is stretching equally in both directions. So IR will be inactive. But if there is an asymmetric stretching, like it is stretching more in this direction, it is stretching less in this direction, then there is a change in the dipole moment of the molecule, IR will be active. And you can just remember a rule called the mutual exclusion principle, which is saying that for a symmetric molecule, when IR is active, Raman will be inactive and vice versa. So when there is symmetric stretching, there is no change in dipole moment, IR is inactive, that means Raman will be active. And if it is asymmetric stretching, that means there is a change in the dipole moment. So IR will be active, Raman will be inactive. So you can remember it in that way. And if there is a bending of the molecule, again dipole moment is changing. So IR will be active and Raman will be inactive. So the rule is basically saying that in symmetrical molecules, whenever IR is active, Raman is inactive and vice versa. So Raman spectroscopy will also tell you about the different bond vibrations, but it has some advantages over IR, is that this symmetric stretching, you cannot study it by IR, but you can study it by Raman spectroscopy. And Raman spectroscopy, normally the intensity is lowered. So you can increase the intensity of Raman spectroscopy using some techniques. One technique is the resonance Raman spectroscopy, where normally Raman spectroscopy, you just supply a certain energy and you see how the scattering is happening. But in resonance Raman spectroscopy, the energy supplied is the same as the energy difference between two electronic levels. So whenever you supply that energy, then the intensity of the scattering will always increase, because in normal Raman spectroscopy, the energy supplied is not equal to the energy difference between any two states. So the molecule is just getting hit by this radiation and it is immediately scattering it. But in resonance Raman spectroscopy, the energy supplied is equal to the energy difference between two states. So now the molecule can properly absorb the radiation and it can emit it properly. So then the intensity increases by 10 to the power 2 to 10 to the power 6 times when resonance Raman spectroscopy is done. And another way to increase the intensity is called surface enhanced Raman spectroscopy, where you have certain molecules. So the molecule is causing Raman spectroscopy, but if you cause the molecule to be adsorbed on the surface of some nanostructure, we don't need to look into why this is happening. You can just imagine that if you have the molecule loose, then the intensity of Raman scattering is low. But if you make the molecule adsorbed on the surface of some nanostructure, then the intensity of this scattering increases by 10 to the power 10 to 10 to the power 11 times. So you can imagine how much the intensity is increasing. Just instead of taking the loose molecule, we make the molecule adsorbed on some nanostructure surface. So it increases the intensity by 10 to the power 10 to 10 to the power 11 times, which is a huge increase in intensity. That is called surface enhanced because it is being enhanced due to this being adsorbed on the surface. So it's called surface enhanced Raman spectroscopy. And So like I mentioned that, so this is like I mentioned that in FTIR, you can use FTIR to predict how much contribution is there from each secondary structure. You can also use Raman spectroscopy to predict that. So there are certain software where you can input the Raman spectroscopy spectra, and it will deconvolute the spectra. It will tell you that say one peak is due to, you can see there are very characteristic peaks due to the different secondary structure. So similar to how from CD and FTIR the secondary structure could be predicted, from the Raman spectroscopy also the secondary structure can be predicted using software. And there are characteristic peaks like we saw in absorbance and fluorescence spectroscopy. The aromatic amino acids showed very characteristic peak. In the Raman spectroscopy also, the aromatic amino acids, phenylalanine, tyrosine, and tryptophan shows very characteristic peaks. And we can couple a Raman spectrometer with a microscope. So this is called, what that will do is that using the microscope, we can focus on a very small region of the sample. And if we couple the microscope with a Raman spectrophotometer, then we can carry out Raman spectroscopy in that microscopic region. So suppose we have a cell, and in that cell we want to carry out Raman spectroscopy only on the nucleus. Then we can focus the microscope on the nucleus, and because the microscope is coupled with the spectrometer, we first focus the microscope on the nucleus, and then whatever the microscope is focusing on, the spectrometer will hit that particular region with the radiation. So only the nucleus is getting excited, and we can carry out Raman spectroscopy only on the nucleus. So we can couple a Raman spectrometer to a microscope to magnify the sample we are visualizing and carry out the Raman analysis on one particular region of the sample. And we can also use Raman spectroscopy to study the events that are happening inside a crystal. So basically, this is, one second. Yeah, so this was Raman microscopy, where we coupled a microscope with a Raman spectrophotometer. Another one is the Raman crystallography. So these are applications of Raman spectroscopy. One was the Raman microscopy, where we are coupling the microscope with the Raman spectrophotometer. Another is the Raman crystallography, where we are mounting a single crystal. So you can see that there is a single crystal, and on this single crystal, we are focusing the, so we have the Raman spectrophotometer focused on that single crystal. So we know that Raman spectroscopy can be used to see very minor changes. And so when we are focusing the Raman spectrophotometer on that single crystal, we can study the changes happening in the crystal. So if you remember, few classes back, we had seen that when a protein is in a crystal, even then the protein can act as an enzyme. So suppose we have a protein enzyme in a crystal, and we are adding some substrate, then the enzyme will convert that to the substrate to the product in the crystal itself. So if we focus the Raman spectrophotometer on the crystal, we can observe the chemical changes happening inside that crystal in real time. So in X-ray crystallography, we know that we can not observe the changes in the crystal. We can only study the particular orientation of the crystal. But if some chemical change is happening inside the crystal, like the enzyme is converting the reactant to the product, then we can study that using Raman crystallography. We have to focus the Raman spectrometer onto that single crystal, and we can see what changes are happening inside the crystal in real time. So that is another application of this Raman spectroscopy. Now we'll go through some practice problems. One is asking, which is the significant peak of an alpha helix in CD spectroscopy. So if you remember this graph, you can see that alpha helix will basically have one positive peak at 193 and two negative peak at 208 and 222. So in these three, the only peak that is there in the option is the 222. So the correct answer is option D. Then it is saying chemical events within the crystal can be obtained from which of the following technique? Here, the answer is Raman crystallography. That is what we studied in the last slide before the questions, that in Raman crystallography, we can focus the Raman spectrometer onto a single crystal and study what are the chemical changes happening inside that crystal. So the correct answer for this is Raman crystallography, which we can use to study the changes happening in a single crystal. Then this is saying, calculate the Stokes shift of a molecule that has excitation and emission wavelengths at 280 and 340 nanometer.
60.
So if you, yes, it is 60. So that is like what we discussed, that Stokes shift is the difference between the absorption and emission. So that is option C. Then you have this asking that which mutation in the wild type green fluorescent protein is responsible for the enhanced phenotype. So GFP is green fluorescent protein, EGFP is the enhanced green fluorescent protein. This again is something you have to remember. Green fluorescent protein was happening due to this serine, glycine, tyrosine trio of amino acids. And the enhancement of the fluorescence happens when we mutate the serine to threonine. So it is option A, where serine is mutated to threonine. Then this is asking just about the order of the increasing wavelength in the electromagnetic spectra. So if you remember, the highest wavelength is for the radio waves, and then IR, then visible, then UV, and lowest wavelength is the X-rays. So option B is your correct answer.
Ma'am, option C is also correct.
No, ultraviolet is less than visible, no? See, radio, infrared, then visible, ultraviolet wavelength is lower than visible. So in option C, it is showing opposite, no? Like ultraviolet and visible are switched. Yeah. Then the question is that what is the unit of absorbance?
No unit.
Yeah. So absorbance is a ratio. So intensity, whatever unit is there, it is cancelling out. So the unit of absorbance doesn't have any unit. So the answer is D. Then it is saying that what is the unit of ellipticity in CD spectroscopy?
That is also no unit.
No, actually that is B. So if you remember ellipticity, we are seeing the what you are saying is that absorbance has no unit and CD is difference between the absorbance, so it should have no unit. It appears to be true, but actually what we put in the y-axis is ellipticity value. So this angle we are putting in the y-axis. So if you imagine this upper arrow as the right polarized light and this blue arrow as the left polarized light, then what we actually plot in the y-axis, I'll go to one of the CD plots actually, you can see. So what we plot is the ellipticity, and that unit is actually degree. So
Degree per molar.
Yeah, so if it is molar ellipticity, it will be per molar. If it is only ellipticity, it will just be degree. So here we are talking about only ellipticity. So the unit is degree or millidegree, whichever you want to take. So that is why the unit is B, which is millidegree. If it was saying molar ellipticity, then it will be millidegree per mole. This is asking that what is the relationship between the intensity of light with the sample concentration?
Directly proportional.
Yeah, which is A, that is directly proportional. So intensity of light, that is the absorbance, is directly proportional to both concentration and path length and the molar absorptivity. And the last question one sec. Yeah, it is asking that molar extinction coefficient is dependent on which parameter? So
Concentration.
no, see, molar extinction
Okay.
coefficient is actually dependent on wavelength only. So concentration will change the absorbance, but molar extinction coefficient is does not depend on any property of the molar extinction coefficient is only dependent on two things: the identity of the molecule, that is each different sample will have a different molar extinction coefficient, and the wavelength. So here the
But
molecule is
in that case, the molar extinction coefficient remains always constant. So how it will depend in the, how it will depend on wavelength lambda? It
uh,
can depend on the sample, but lambda.
actually it is think about it like, I'll go back to the UV visible spectroscopy. So actually, so you remember when I was talking about this slide, I said something called the probability of transition. So the probability of transition is basically dependent on the molar extinction coefficient. Because the molar extinction coefficient of these two is high, these two are the main transitions observed. These other transitions, if you calculate, again, I'll show you the table later, the molar extinction coefficient of the other absorptions are low. So the net absorbance intensity is also low. So the other transitions become less important. So actually, like this, even within the same compound, the molar extinction coefficient will vary depending on the wavelength. That is this energy difference between the energy levels. So if you can, this was one graph that was there. So this graph, if you can see, four different compounds, they have different molar ellipticity, but the molar ellipticity is also varying with the wavelength. So it actually depends on two factors, both the wavelength and the identity of the compound.
Okay.
And finally, it is asking that which amino acids are responsible for the absorbance at the 280 nanometer. So this is your aromatic amino acids.
Heat,
That is your option.
50% tyrosine.
Yeah. So actually, there are too many topics covered in this class. I can understand. That is why towards the end, I had to speed up a little bit. So I will upload the slides and the video. You go through it again, especially the last slides where I had to speed up a bit, and you can ask me all your doubts. Like you can mail me. I gave you my mail. You can just write, can you explain slide number this in the next class? So next class, I will focus on that slide a little bit more. Actually, so many topics are getting covered that I cannot explain each in that much detail, but you go through the slides and you can just send me the slides numbers which you think need to be explained again.
Okay.
So yeah. Okay, so I'll end the class here.
Thank you, ma'am.
Okay, thank you.